In our first example of Chapter 14, we'll examine the concept of solubility. Remember the rule of thumb, like dissolves like? Well, we'll use that rule of thumb here to perform a qualitative analysis and determine whether some molecules are fat or water soluble. Vitamins are often categorized as either fat-soluble or water-soluble. Water-soluble vitamins, on one hand, dissolve in body fluids and are easily eliminated in the urine, so there's little danger of overconsumption. Fat-soluble vitamins, on the other hand, can accumulate in the body's fatty deposits. Overconsumption of a fat-soluble vitamin can actually be dangerous to your health. Examine the structure of the vitamins shown here and classify each as either fat-soluble or water-soluble. First, let's consider example A, which is vitamin C. Notice that vitamin C has a lot of polar bonds. We see carbon-oxygen bonds, which we know are polar because oxygen is the second most electronegative element on the periodic table. And here we have an OH bond that we know is a hydrogen bonding type of bond, so it can offer hydrogen bonding. It's an alcohol functional group, as a matter of fact. So we have several different polar bonds in this molecule. And because the molecule is surrounded by all of these polar bonds, this molecule is water soluble. Now let's consider vitamin K3. Notice that most of the bonds in this molecule are carbon-hydrogen bonds, and we learned in our lecture that carbon-hydrogen bonds are nonpolar. We do have two carbon-oxygen bonds, and these are extremely polar bonds, these carbon-oxygen double bonds. However, we learned last semester that polar bonds in opposite directions cancel each other out and lead to overall nonpolarity in a molecule. Therefore, vitamin K3 is nonpolar and fat-soluble. Next, we'll consider example C, vitamin A. Vitamin A has almost all carbon-hydrogen bonds. There is one OH bond, a small alcohol functionality in this molecule. However, it's very small. It has a very small polar bonding area compared to the nonpolar bonding area that the rest of the molecule takes up, and that makes vitamin A fat soluble. Next, we'll consider vitamin B5. Notice that vitamin B5 has a lot of polar groups. In fact, it's basically surrounded by these polar groups, leading to vitamin B5 being more water soluble than fat soluble. Next, we'll consider whether these molecules are soluble in hexane. First, we have water. Water has the molecular formula H2O, and we learned last semester that water has these four groups attached to it, and therefore the electron pair geometry is actually tetrahedral, but the molecular geometry is bent. And because we have this bent geometry with the oxygen-hydrogen bonds, these polar bonds don't cancel each other out, and water has a net dipole going straight down through the center of the molecule in that direction. So water is polar. And let's consider hexane. Right here. And so hexane is nonpolar because it doesn't have any polar bonds. Therefore, water is not soluble in hexane. Part B asks us to consider propane. Propane has 3 carbons with its respective hydrogens, and therefore propane looks a lot like hexane, and therefore propane is soluble in hexane. Next we'll consider ammonia. Ammonia has the molecular formula NH3, so let's draw the structure for ammonia. Ammonia has a lone pair, the nitrogen has a lone pair, and it has a hydrogen going back, a hydrogen coming out, and a hydrogen in the plane of the board. We learned in our chapter that nitrogen-hydrogen bonds are polar. In fact, nitrogen-hydrogen bonds exhibit hydrogen bonding. So the nitrogen is withdrawing electron density from the hydrogens, leaving a partial positive on the hydrogens and a partial negative on the nitrogen. Additionally, we have this lone pair here, which is adding even more electron density to that end of the molecule. So ammonia is a polar molecule. Therefore, ammonia would not be soluble in hexane. The next problem asks us to consider HCl. Hydrogen has an electronegativity value of 2.1 and chlorine is 3.0 with a difference of 0.9. Anything greater than 0.4 is considered to be polar, and so this is a polar bond, and since there's only one bond in the molecule, this is a polar molecule, and therefore HCl is polar and not soluble in hexane.